So welcome back, students. In the last videos, we derived an expression for motional EMF, and then we also did some problems with that. I'm going to expand on it in this video. If there is potential involved, then clearly there will also be energy involved. And if it's energy involved, then there will be power involved. And we are going to study this energy and power involved in this video quantitatively. We are going to assign numbers to it. So even in the previous video we talked about current. We said current is generated in one direction, but then we didn't say what was the value of the current. So we'll talk about all that now. We'll talk about the current, we'll talk about the energy and power, about the motional EMF, which we studied a couple of videos before. So what did we do in that video? We said there is a magnetic field which I marked in red, which is going into the board, and there is a rail. There are actually two rails, okay, and connected by this rod conductor. This fixed. This setup is fixed. The rails are fixed, and this conductor which is connecting those rails is also fixed. And there is a sliding rod on the rails which can move on the rails. So I can move the rod in this direction or in that direction because it is sliding on the rails. So using this, we explain that the EMF induced in this will be BLV. So this is what we derived. And we also said that because of this, there will be a current going in this circuit. So the direction of the current is this. That is very clear, because you can see that as a rod is moving in this direction, clearly the flux in the loop is decreasing. If the flux in the loop is decreasing, then you must be increasing the flux. The current which is flowing through the circuit must be increasing the flux. So you must put flux in this direction, the same direction as the external magnetic flux. So I have to put the flux in this direction, so the current must be flowing in this direction. So clearly I will be flowing like this. So this is what we said. And as I said, the induced EMF is BLV. Okay. And there is this current I flowing. Now notice this. This current I is flowing in an external magnetic field, which means that the conductor must experience a force, the Lorentz force. F is equal to ILB. That's the force it must experience. And in which direction will the force be? Well, let me take this segment QS. Current is in this direction. Flux is going into the board. So I into this length, cross B will be down. So the force will be in this direction, on this segment. So I'll call it as FSQ or FQs. FQs. What about FSR? Goes there. I is in this direction, B is into the board, I'm this length, not this length, this length. IL cross B, it will experience the force in this direction. So FRS will be in this direction. FSR will be in this direction. Let me take this segment. RP. So I is in this direction, B is in this direction, so IL cross B, force will be up. On this, then the force will be F RP. And what about this? PQ. FPQ will be down. Current along PQ is down, so B is there, so it will be down, B is here, so IL cross B would be in that direction. So the force on this would be in this direction. F, P, Q. And notice that is, we said only this is movable, this is sliding, and all the others are not movable, fixed. Which means this force would be countered by a force of friction or another external force. It's like that, like it's like fixing this on a, say, on a wall. So if it tries to move, then because you fix it on the wall, then that will, the wall, the friction of the wall, the friction of the wall will exert a countervailing force. So this won't move. It may experience a stress, but it won't move. Okay, and so is the case with this. This is also not moving. This is also fixed, and this is also fixed. These rails are also fixed. So these three parts won't move because they are fixed, and there is a countervailing force acting on each part. It could be friction, or it could be any other external force which does not allow these three to move. But what can move? Only this, because that is sliding. So only if it experiences a force, then only this is going to be affected by that. All the other segments are fixed. Only this is movable. Okay? So I can ignore these because even though there are forces due to the current and the magnetic field, they are going to be balanced by some other force, because we say that this setup is fixed, but this is not. So this will experience a force just because it's moving. There is nothing to balance this force now. So then this will be affected by that force. So that is the force we are going to calculate. Okay, even to before we even calculate the force, okay, what is the force now? What is the force? FPQ is equal to I L. L is this length, right? This length. We said it's that length, IL. And then B is the magnetic field strength, ILB, IL cross B. Okay, IL cross B. Either by ILB sin theta, ILB sin theta, and then theta in this case is 90 degrees. It's down. And that is into the board. Current is down, B is into the board, so this is 90 degree. So I get simply ILB. That's the magnitude of the force experienced by this in that direction. Okay. Okay. But what is I? What is I? Well, this BLB is the EMF induced in this circuit, and if, say, R is the resistance of the circuit, then I can say that the current flowing through this loop would be by R, that's going to be equal to B LB by R. That is the current. So if I know this, then I can calculate the force experienced by this sliding rod. So then FPQ written as BLV by R into L to B. So that would be equal to B squared L squared V by R. So this is the force experienced by this conductor. See, that is understandable. The conductor is trying to move in this direction. The PQ rod is trying to move in this direction. And there is a force which will act on it. It will try to slow it down. And if I want to continue to move with that velocity v, then I must provide this force so that it will continue with velocity v. Otherwise, what will happen? So it will start with velocity v, and as it moves into the field, it's going to experience a force that will retard this motion and then stop it at some time. So that makes sense too, because once you get in, when you get in with some amount of kinetic energy. So this will have a mass m, this rod will have a mass m, that has a velocity v. So F mv squared is the kinetic energy with which you enter. And if you don't supply any other energy, okay, or any other force to counter this, if you don't supply a force to counter it, then what will happen? You get in with the kinetic energy, F mv squared, then it's going to slow it down, so it will move in this and then stop. But as it is moving, it will be generating a current I, and that current will produce heat, I squared R. That heat would be equal to the kinetic energy with which you got it, the I squared R into T, obviously. Okay, the time, I squared R is power, and then T is time. If you multiply the time for which it was moving, then you get the energy, and that energy must be equal to the energy with which you came in. And that I will also be changing in that case. Why? Because you come with V, but this is slowing it down. As it slows it down, then if you start with say 10 meter per second, then it will become 9 meter per second, 8 meter per second, 7 meter per second, come down, and finally it will stop. So the V will also be constantly changing. As V is constantly changing, your EMF will also be changing. Okay, so finally it will come to a stop. But as it was moving into the field before it came to a stop, there was a varying EMF which was generated. Because varying EMF, because V will be varying, you are slowing it down. Okay? Varying EMF is generated. So there is a varying current that is also generated in this decreasing current, clearly. Okay? Generated, and that current would have produced an I squared R power loss. And if it is moving for a time t, then I squared R into t will give you the total energy. And that total energy must be equal to the kinetic energy with which you enter. Like this. I give it some amount of kinetic energy, so it will have half mv squared. So there is this slowing down process, gravity is pulling this down. So then clearly it comes to a stop here. Okay. So in that case you will have potential energy. Okay. And because of potential energy, then again it gets converted into kinetic energy in this case. Okay. But here what happens is that kinetic energy with which you enter, it gets converted into heat. When you dissipate energy, then it will come to a stop. That's it. In this case, it won't oscillate. It will come to a stop because there is no. When it comes to a stop, why does it come to a stop? Because there is no current flowing. If there is no current flowing, there will be no force. Obviously, so that's the reason. It will come to a stop, and in the process, heat would have gone out. This would have generated heat. I squared R losses would have generated heat, and that heat would have escaped to the universe, to the earth, around the atmosphere, and from there finally heat will move out of the earth. Okay, so that's That's what happens. So there is a law of conservation of energy. That is what. Okay, so if you don't want it to stop, then what should you do? If you don't want it to stop, then you have to provide this force, this direction. You have to balance this force, because as it's trying to move, as this rod is trying to move in this direction, the force is acting in this direction, it's trying to slow it down. So you have to counter it, you have to push it now. So if your pushing force is equal to this FPQ, then it will continue to move with velocity v. I want you to understand that. So as it starts moving into this, there is a force acting on it, that is FPQ. It's going to slow it down. But if you don't want it to slow down, then you have to provide an equal amount of force in the opposite direction so that it continues to move. So in the same direction with the same velocity. It won't slow down now. It starts with V, there is a force acting on it, then you balance that force. Then you keep balancing it. So the net force on it will be 0, so it will continue with that velocity V. That's the case we are going to take, because you are going to do work against this force. Then what is the work that you have done? That's the question. Okay? Suppose you balance this with the same amount of force. What is your force? I'll say this is my force. F Swaminathan. Okay? F Swaminathan. That is equal and opposite to this force. So I can take this magnitude. That doesn't change because I am providing the same amount of force. So my force would also be equal to this. So B squared L squared V by R. That's my force. Okay? Then what is the work I am going to do? So what's the work I am going to do? The work done by me, work done by Swami, it is equal to, say, what is work done? Force into distance, right? Force into distance. So I'll say force of Swami dot the distance over which this was acting. The force and then the displacement, if you see, they are in the same direction, so cos theta would be 1. So there is no difference. So cos theta, FD cos theta, I'm going to take it as cos theta is 1, so FD. Okay? So, okay, L expand F dot D. So that is equal to F Swami into D. That's what it is. D is how much what distance I travel from this position. This will be my origin. So D is in this direction. It's my D. Okay? So that's what I should do. This is the work I do. Then what's the power? Power of Swami is equal to work done by Swami, the time. Right? So it's going to be D work done by dt, and that's going to be equal to F Swami. That's a constant. Notice, because this is a constant. B is a constant, L is a constant, V is a constant because we are not changing the speed, and R is a constant because that's the resistance in the circuit. Okay, we assume that these rails don't have any resistance, only this conductor has some resistance. So that's the reason. So that will remain constant. Okay, F Swami into now D dt. Okay, this is like dx by dt. So what is that? What is this quantity? dt by dt. Dx by dt. That is v, velocity, the speed with which this distance is changing. That's velocity. So so this is going to give me F me into this speed finally. So the power is this. So now can I calculate the power? So the power is going to be equal to the power I need to provide is going to be equal to this one, equal to F is B squared L squared V by R into V. So I'm going to get V squared L squared V squared by R. So the power I generate is equal to B squared L squared V squared by R. Okay. Well, I said that this will go as heat produced in the circuit. Let's say if I is the current which is flowing through it, then what's the power looked at from the perspective of the heat produced? Let's see this, the heat produced. Heat produced. So what is the power? It's equal to I squared into R, right? I squared into R. So we know this. V into I or I squared R is the power in an electric circuit, the heat generated in the electric circuit goes as the heat loss. So I is this BLV by R. Okay, so this is going to be I squared into R. So it's going to be B squared L squared V squared. This is R squared and you're multiplying it by V. So R squared into R, so I'll get R. So this is the heat, the I squared R loss. Notice that both are same. So I generate this power by pushing the rod against this force, the Lorentz force it's going to experience because there's a current flowing in it. And now that is equal to the heat produced, that power, the I squared R losses. So the power I give here goes to produce the I squared R loss, which is heat in the circuit. So the law of conservation of energy is obeyed. Hope this is clear to you. Now, okay, now let's do example 6.8. Let me read the problem. Refers to a figure is given. Refers to figure 6.12a. The arm PQ of the rectangular conductor is moved from x is equal to 0 outwards. The uniform magnetic field is perpendicular to the plane and extends from x is equal to 0 to x is equal to b and is 0 for x greater than b. Only the arm PQ possesses substantial resistance R. Consider the situation when the arm PQ is pulled outwards from x is equal to 0 to x is equal to 2b and is then moved back to x is equal to 0 with constant speed v. Obtain expressions for the flux, induced EMF, and the force necessary to pull the arm and the power dissipated as joule heat. Sketch the variation of these quantities with distance. Okay, so this is the figure given. I'm going to draw the figure. This example 6.8. So this is the magnetic field which is coming out of the board. So that's why you have the dot. Dot meaning you see the arrow head. So it's coming out of the board. If it is a cross, then it means it's going into the board, but now you have a dot. So field B is coming out. So the arrows are coming out of the board. And so they have this setup. The setup we have for the motional EMF, you have two rails connected here, and so this is, and you also have a, let's say, a sliding rod on it. So this is P, this is Q, and R, S, and this length is L. Anyway, so this is their 0, this is x is equal to 0, and this extent, the field is from this position to, this is x is equal to B, that's the distance, this is distance B, okay. And what is happening is that, like, you take this rod, this metal sliding metal rod, you start from 0, you move to 2B. So B, then is another B. So this position is actually x is equal to 2B. So you are going to move the rod to here. So you start sliding the rod from this position RS, which is 0. Then you go all the way up to 2B, and then you come back again with a constant speed V. That would be, I'll draw this. The speed is V, but this is not in one direction actually. So you start from here, you go all the way there to 2B, and then you come back again. So in that process, they want you to find the flux, the EMF, the force, and then the power. All the four things are what they want now. So we'll do the graph for them. First, let's see, what about the flux? The flux would be, let's see, the flux phi B, right? It's magnetic flux, so we call it as B. So that would be, if it is here, then the flux inside the loop will be 0, because there is no area for that loop. If this rod is here, then the area is 0, or the loop is 0, so there will be no flux which goes through that area. But then as you keep increasing, then this changes. So there is flux that is changing. Okay, and what is that flux? Suppose I take some distance x. Let's say this is my distance x. Okay, so what would be the flux which goes through this loop? That would be, if B is the strength, magnetic field strength, and if L is the length and x is the width, then it will be the breadth, and it will be L into x. So that would be the magnetic flux which is going through this area, because it's B into A. So B is the B we have taken, and then Lx is the area of that loop at any distance x from the origin. So this would be the flux through this when x is greater than or equal to 0 until it is equal to B. Up till here. Sorry, yeah, B. B is this one. So this would be the value. As x increases, the flux also increases. As x reduces, then flux also will reduce through this area. But beyond that, beyond this, so if x is greater than B, then suppose this is here. What's the flux through the loop? Only this flux, right? Nothing else. You are not adding anything. after you move this away from this position. Up till here it changes, notice. The flux through the loop is changing. But once you go beyond this, then the total flux in the loop remains the same wherever you go, from this point forward. So I will say that B into L into B, B, L, B, for any distance of x which is greater than B, right? Greater than B, or if I can adjust it, I will say that it is less than B, and I will say it's included. Doesn't matter, it's the same thing, right? Greater than B and less than or equal to 2B, because 2B is the farthest distance you go to, so 2B. This is the expression for it. And if we were to draw the graph for it, how will it be? So I'll have the distance x here, x in this, and this will be my 5D. Okay. So this is going to be B. This is going to be 2B. Okay. And let's see how is it going to look like. When I start, this is, it will be 0. As x increases, this will also linearly increase, right? B and L are fixed, so it's linearly, x is only variable, linearly increase up till this one, B. Okay, it will linearly increase up till here until you reach B. So this point would be, what's the value? BLB. BLB. So that's the value here. And after this, you move further. Again, that doesn't change. Like till only this flex is there. Even if you move here, only so much flex is there. You are not adding flex to it after you go out of this. Then that will remain constant. It will remain constant. It will remain in that position. BLB only. Now you come back. That's the second part, right? You go from here to 2B and then again come back to 0. That's the condition. So when you come back, 2B, from 2B to B, how will it be? As you come back from 2B to B, come back from 2B to B, it will still remain the same. There won't be any change. But then once you reach B, as you come inside, notice the flux is going to reduce like this, you know, and it will become 0 as you reach here again. So if I put 0 here, from B to 0, x is equal to 0, and that will come down. Okay. So this is a graph of the flux. Okay. So that's the first part. What is the second part? This is the first part. 1. What's the second part? The second part is determining the EMF. So what's going to be EMF? The EMF E, let's see, that's equal to the rate of change of flux, right? So the rate of change of flux. So let's see, from 0 to B, what are you going to get? From 0 to B, this is, the flux is increasing. So if the flux is increasing, then d phi by dt you will get a positive value. But what is E? E is negative of d phi by dt. So this is actually BLB. This will be BLB, right? BLB, we know. Yes, BL, dx by dt will be V, with which you go. That's what it is. But as you do that, it is increasing, right? If it is increasing, then you must decrease it. So if d phi by dt and minus d phi by dt will be minus BLV for what values of x? For x greater than 0 and less than b. Beyond b, so you reach here, and after this what happens? We go like this, but does the flux change? The flux doesn't change. Once you come here, it will remain the same. If you are at any position between this point and this point, you see the flux is changing. Flux through the loop is changing. But once you come out of it, the flux remains constant. The flux remains the same. So d phi by dt will be 0. So there will be no EMF induced. So EMF will be 0 for what? For x values greater than or equal to b until it is 2b, because that's the farthest you go to. So from here to here, the flux through the loop does not change with time. So your E will be 0. And when you come back, let's see, when you come back, E, when you come back, what's going to happen? As you come from 2B to B, the flux is still not changing. So as you come from 2B to B, the flux is still not changing. But when you go from B to 0, the note is here, sigma, where E is equal to same BLB, but this time this will be positive. Why? Because the flux is reducing. So d phi by dt a negative number, and minus d phi by dt, which is E, will be a positive number. That's BLB. So if you were to draw that again, a picture, my x, and then this is my E. Okay, so how would it be? From this is my B, this will be 2B, from 2B to B, and B to 0. So those are the 4 parts. Let's see. So from 0 to B, as I move away, I am going to have a negative thing. It's a constant, negative. So it's going to be minus BLV. That's my thing. And from B to 2B, it's going to be 0 because there is no flux change after that. So it suddenly drops to 0. Then it is 0 like this. Okay? And from 2B to B again, it is 0. As you come back also, it is 0. But from here, from B to 0, as you do that, then it will go up. So this will be, and say that will be positive. BLB. Okay, So this is the structure of the graph for the induced EMF versus the distance. Okay, now let's look at the third part, which is the calculation of force. The force equation is this, right? Okay, force is equal to B squared L squared V by R. Okay, this is over this distance. Actually, so we know the current will be constant. So from starting from here till B, you will have this force. So x value is greater than or equal to 0, and then that's going to be less than B. So after here, then you will have this B squared L squared V by R. That's what you will have. And once you go out of this, more than B and less than 2B, the force value is going to be 0. But in which direction would it act? Okay, I got the force is ILB for the most part. So, like and it's also going to oppose motion, right? So you are taking it away like this towards the positive x, in the positive x direction. So the force would be acting in the opposite direction. So this is something that we discussed a short while ago. So the force is going to be in this direction now, because we are moving it in this direction. So force should oppose motion, and this would be negative. I'll just take it as negative one. Okay. And then you go there, and you come back from. Force will still be 0 when you come from 2B to B. So from 2B to B, the force will still be 0. And once you get in here, the force will be equal to B squared L squared V R. But what's the direction now? Now this is moving in this direction. If this is moving in this direction, the force must be acting in the opposite direction. It should slow it down. So that would be in the positive x direction. So this is going to be positive. And if you were to draw the graph, then it will be like this. This is a force, and this is x direction. Let's say it's A, it's 2A, from 2A to A, coming back now, and A to 0. So this is how it is, right? So in that case, this is a constant. B squared, L squared, V and R are all constants. So, but then you are going to have a negative. Okay. So the value will be minus B squared, L squared, V by R. And from A to 2A it is 0, from 2A to A again 0, and there you are going to get a positive. Okay. So this would be again B squared L squared V by R. So this is how the graph for the force would be. And what about power? So if we have to do power, which is 4, power is given by the expression B squared L squared then B squared by R. That's power. And the work done is always positive, right? Because when you push it this way, you are going to do work against this opposing force. So like the work you do is in the same direction as motion. So it's positive. So for the x value 0 greater than x value is greater than 0 and less than b, this is going to be a positive value, b square a square b square by r. And this, once you cross b, then move from b to 2b, it's going to be 0. You don't have to do any work. Then you come back from 2b to b. There is no field, there is no work you need to do against anything, there is no force opposing you, so clearly b is equal to 0 when you come from 2b to b. And from b to 0, again you are pushing it in this direction, the force is opposing you, but you are applying the force in the same direction, so this is going to be positive again. You are doing positive work in this case also. So that would again be b squared a squared b squared by r for motion from b to 0. So if you were to draw the graph for this, again, so this will be x and this will be toward this direction, and so this is going to be a, then 2a, then 2a, 2a, then a to 0. So for all these things, you can have just like the value would be b squared a squared b squared by r, so that would be this. So let's say this is b squared l squared b squared by r. So this is going to be positive from 0 to a, and a to 2a will be 0, and 2a to a 0 again, 0, and from a to 0 then you will get again positive. So this is how the graph will look like, and this is how we do this problem. Think about it. Try to understand what's being done, and it's because it's a very important problem, and if you can do this, you can do many other problems too. If you can do it properly and you understand the concepts well, that's what it means. I hope it's clear to you.